We live in a universe governed by laws. For over a century, two grand theories have served as our primary guides, and they have been spectacularly successful. One theory, a masterpiece of a single mind, describes the universe on the grandest of scales. The cosmic ballet of stars, galaxies, the very fabric of space-time. This is General Relativity. The other theory, a collaborative triumph of many brilliant minds, describes the universe on the impossibly small scale of atoms, particles, a realm of buzzing uncertainty, strange connections, that is, quantum mechanics. Together, they are the twin pillars of modern physics. Yet there is a deep and unsettling problem. They don't get along. Imagine you have two master blueprints for building a skyscraper. One blueprint describes the foundation, the steel frame ensuring the tower can withstand hurricanes, earthquakes. The other blueprint describes the electrical wiring, plumbing, ensuring every light switch and faucet works perfectly. But when you try to lay one over the other, the lines don't match up. The plumbing runs through solid steel beams. They are both right, yet they contradict each other. This conflict is often hailed as the single biggest crisis in fundamental physics. It's a chasm that separates our understanding of the very large from our understanding of the very small. For decades, the smartest people on the planet have been trying to build a bridge across this chasm, a single theory that would unite gravity with the quantum world. They have developed incredibly complex and beautiful mathematical structures, strings, loops, in an attempt to reconcile the two. These efforts are heroic, but the chasm remains. The two great theories, both tested and proven true in their own domains, continue to tell us fundamentally different stories about the nature of reality. What if, just what if, we've been looking at the problem from the wrong angle? What if the conflict isn't a sign that we need to build an elaborate new bridge between two perfectly good cities? What if, instead, it's a sign that one of our cities was built on a foundation we don't fully understand? Perhaps the problem isn't that the theories are incompatible, but that our grasp of one of them, gravity, is incomplete. This essay explores a bold but simple idea, that some of the weirdness of quantum mechanics might be a symptom, a consequence of our limited understanding of how gravity and space behave at the tiniest of scales. Let's take a moment to appreciate the sheer elegance of the first great theory, general relativity. Before Albert Einstein, we thought of gravity as a mysterious force, an invisible rope pulling objects toward each other. Isaac Newton gave us the math to calculate this pull, planets, cannonballs. But he never explained what gravity was. It was just there, an action at a distance that somehow reached across the vast emptiness of space. Einstein came along and changed everything. He offered a revolutionary new vision. He told us that space-time are not just a static, empty stage where the cosmic drama unfolds. Instead, space-time is a dynamic, flexible fabric. Imagine a stretched-out rubber sheet. If you place a heavy bowling ball in the center, the sheet will bend and curve downwards. Now, if you roll a small marble nearby, it won't travel in a straight line. It will follow the curve created by the bowling ball, spiraling inwards. Einstein said this is what gravity is. Massive objects like the sun don't pull the Earth with an invisible rope. Instead, the sun's immense mass warps the fabric of space-time around it, and the Earth is simply following the straightest possible path through that curved space-time. Gravity is not a force, it is the geometry of the cosmos itself. It is the shape of reality. This idea is breathtaking in its scope and beauty. It explains why light from distant stars bends as it passes by our sun. It predicts the existence of bizarre objects like black holes, regions where space-time is curved so intensely that not even light can escape. It accounts for the subtle wobble in the orbit of Mercury, a puzzle that Newton's theory couldn't quite solve. And it forms the basis of our entire modern cosmology, describing the expansion of the universe from a hot, dense beginning in the Big Bang. General relativity is a theory of the smooth, flowing, and continuous dance of space-time on a cosmic scale. However, Einstein's theory describes a world that is fundamentally predictable and continuous. If you know the position and speed of a planet, you can calculate its path with exquisite accuracy far into the future. The universe, according to relativity, is a grand and intricate clockwork mechanism where the gears are the very contours of space and time. There are no sudden jumps, no inherent fuzziness, no fundamental limits to what you can know. Space-time is a smooth landscape, and everything follows the curves. This philosophical underpinning, this vision of a smooth, deterministic reality, stands in stark contrast to the world described by our other great theory. Now, let's journey from the cosmic expanse down into the unimaginably small. Here, in the realm of atoms, electrons, photons, a completely different set of rules applies. This is the domain of quantum mechanics, a place of profound strangeness and wonder. If general relativity is a majestic waltz, quantum mechanics is a frenetic, unpredictable jazz improvisation. It doesn't describe what things are and where they are going with certainty. Instead, it deals in probabilities, possibilities, inherent fuzziness. The universe has a built-in element of chance. One core idea: particles like electrons don't have a definite position until you measure them. Before you look, an electron exists in a superposition, a cloud of possibilities. It is, in a sense, in many places at once. Only when an observation is made does this cloud collapse into a single, definite outcome. It's as if the universe holds its breath, refusing to commit. A baseball in everyday life is always in one place, whether we're looking or not. Quantum mechanics introduces the uncertainty principle. You cannot simultaneously measure certain pairs of properties, like a particle's exact position and its exact momentum, with perfect accuracy. This is not a limitation of instruments, it's a feature of reality. The universe at its core is blurry. The theory describes quantum leaps. An electron can jump between energy levels instantly, never existing in the space between. Despite its strangeness, quantum mechanics is arguably the most successful scientific theory ever created. It is the bedrock of modern technology. Lasers, transistors, microchips, computers, smartphones, MRI machines. Its predictions have been verified to astonishing accuracy. The theory works. It gives us the right answers every single time. So here we stand, with two titans of thought. General relativity gives us a smooth, deterministic, geometric universe. Quantum mechanics gives us a fuzzy, probabilistic, jumpy universe. When we try to apply quantum rules to the smooth fabric of space-time, the mathematics breaks down. When we try to describe the gravity of a single, tiny quantum particle, the equations spit out nonsensical answers like infinities. This is the heart of the conflict. The language of one theory seems utterly incompatible with the language of the other. The conventional approach has been to assume quantum mechanics is more fundamental and that we need to quantize gravity, to break Einstein's smooth space-time into tiny, discrete chunks. But what if we're framing the problem backward? What if the real issue isn't that gravity needs forcing into the quantum framework, but that the quantum framework arose from our ignorance of what gravity is doing at those tiny scales? Gravity is incredibly weak compared to the other forces of nature. On the scale of atoms, its effects are so minuscule, they are completely negligible in almost all experiments. So, for the past century, quantum theory progressed largely by ignoring gravity altogether, assuming that space is just a flat, boring, passive backdrop for quantum phenomena. This is a massive assumption. General relativity teaches us that mass and energy fundamentally alter the geometry of space. A quantum particle, even a tiny one, has energy. Therefore, it must, according to Einstein, be creating its own little warp in space-time. We have never been able to measure this tiny gravitational field, but theory insists it must be there. What if the strange rules of quantum mechanics, the superposition, the uncertainty, the probability waves, are not fundamental properties of the particle itself, but the particle's reaction to and interaction with the dynamic, fluctuating geometry of space-time at microscopic scales? In this view, the weirdness of quantum mechanics is not an intrinsic weirdness of matter, but a reflection of the complex and unknown behavior of space itself. When you zoom in all the way, we see bizarre effects, and not knowing their true cause, we invent a new set of rules to describe them. These rules work. They make correct predictions, but they might be masking a deeper, simpler, more geometric reality. The problem then is not a conflict between two theories, but a profound gap in our experimental knowledge. We have built an exquisite theory of the small by pretending the stage it performs on is perfectly flat and rigid, when it might actually be a wobbly, dynamic trampoline. To make this idea clearer, let's use a simple story. Imagine you are an ancient cartographer tasked with creating a perfectly accurate map of a large, flat plain. You and your team of surveyors use the best tools available, measuring distances and measuring angles with great care. Your map becomes incredibly precise, but unbeknownst to you, in the very center of this plain, there is a large, perfectly smooth, invisible hill. Your measuring instruments can't detect its gentle slope directly. As your surveyors try to lay down straight roads across the plain, they notice strange things near the center. They report back with puzzling data. When we walk in this central region, our steps seem to get shorter, but only in a probabilistic way. We can't seem to measure our exact east-west position and our north-south position at the same time with perfect accuracy near the hill. It's as if knowing one makes the other fuzzy. You, the master cartographer, might be tempted to invent new rules of surveying that apply only to this central region. You might call it anomalous surveying dynamics and write complex equations that predict the strange measurements. The new rules would be a great success. Anyone using your map with the special rules could navigate the plain perfectly. They would arrive at their destinations every time. But those special rules wouldn't be a deep truth about walking or measuring. They'd be a patch, a workaround for the fact your map was fundamentally wrong. You assumed the ground was flat, but it wasn't. The real explanation was the invisible hill. Then a new technology appears, a satellite with an altimeter. It flies over and reveals the hill in all its glory. Suddenly, everything makes sense. You realize you don't need the complicated, anomalous surveying dynamics. You update your map to include the hill's topography. The old, simple rules of geometry work again with the correct curved map. The strange, probabilistic rules were just a shadow cast by physical reality you hadn't discovered. Quantum mechanics could be our anomalous surveying dynamics. A brilliant but provisional set of rules invented because we haven't yet mapped the hills in space-time at the smallest scales. This metaphor of the hidden hill helps us reframe the quantum puzzles. Let's think about the concept of superposition, the idea that a particle is in many places at once until it's measured. In our conventional quantum view, this is just a fundamental property of reality. But what if it isn't? What if a particle is always in one place, but that place is jittering and vibrating because the very fabric of space at that scale is in constant roiling motion? What if space-time itself has a kind of quantum foam or microscopic turbulence that we haven't been able to see? From our distant, macroscopic perspective, the particle's position would appear blurred out, uncertain. It would look like a cloud of probability, because the ground beneath it is constantly shifting in ways we can't track. When we perform a measurement, we are essentially pinning down the particle with a powerful interaction. This interaction might momentarily stabilize the local patch of space-time, forcing the particle and the space it occupies to choose a definite state. The collapse of the wave function wouldn't be a magical, instantaneous event, but a physical process of settling the local space-time geometry. Consider the uncertainty principle. It feels like a strange, almost mystical decree. But perhaps it's something far more mechanical. If a particle's position is tied to the fluctuating geometry of space, and its momentum is tied to how that geometry changes over time, then the two would be intrinsically linked. Trying to perfectly pin down the position might involve freezing the local spacetime, which would, by necessity, make its rate of change, its momentum, completely undefined. It wouldn't be a limit on knowledge, but a fundamental trade-off in a dynamic, physical system. Many core tenets of quantum mechanics could be reimagined, not as fundamental laws, but as consequences of an underlying gravitational dynamic. They are the patches we created to make our physics work where our understanding of space-time is incomplete. This doesn't mean quantum mechanics is wrong. The math is correct. The predictions are accurate. The map with the special rules works. But it might not be the final map. It might be a placeholder for a deeper, more geometric truth that unites the particle with the space it inhabits. Section 7. Water, space, and the illusion of smoothness. Another helpful metaphor is to think about water. If you are a tiny creature living on the surface of a vast ocean, your entire world is defined by the properties of water. From a distance, or when dealing with large-scale phenomena like waves, tides, water appears to be a perfectly smooth, continuous fluid. You could develop a beautiful theory of hydrodynamics that describes its flow with smooth, continuous equations. This theory would be your version of general relativity. Now imagine you develop incredibly powerful microscopes and begin to study what happens in a single, tiny drop of your ocean. You would discover a scene of utter chaos. You would see that your smooth, continuous fluid is actually made of countless individual H2O molecules, all bouncing around, colliding, and vibrating furiously. The smooth laws of hydrodynamics would completely break down at this scale. You would observe what looks like random, probabilistic behavior. A single pollen grain floating in the drop would be jostled about unpredictably. A phenomenon we call Brownian motion. If you had no prior knowledge of molecules, you might be forced to invent a new set of quantum water laws to describe this bizarre, jittery world. You would say that the pollen grain's position is fundamentally uncertain and can only be described by probabilities. You might even conclude that there's a magical force making it jiggle. But the real explanation is simpler. Your world isn't continuous. It's discrete. It's made of parts. The strange quantum behavior is just the collective effect of billions of tiny molecular collisions. The deep truth is the existence of molecules. Could space-time be like water? On our scale, and even on the scale of galaxies, it appears smooth and continuous, perfectly described by the fluid-like equations of general relativity. But what if we could zoom in to the Planck length, a distance fantastically smaller than an atomic nucleus? Would we find that space-time itself is not smooth, but is made of some kind of fundamental atoms or quanta of space? If so, then the quantum weirdness we observe in particles might just be the Brownian motion of those particles as they are jostled by the discrete, granular nature of reality itself. The two great theories would then be unified. One describes the bulk fluid, the other describes the constituent molecules. Section 8. The Path Forward. Probing gravity's deepest secrets. If this idea holds any water, it points toward a clear, if incredibly difficult path for scientific progress. It suggests that instead of focusing only on abstract math to unite the theories, we must redouble experimental probes of gravity and space at the smallest scales. The answers may not be a clever equation, but a new piece of data from an experiment never done before. This is a call to action for the experimentalists, the builders, the tinkerers. First and foremost, test gravity in the microscopic realm. This is monumentally challenging because gravity is so astonishingly weak. The electromagnetic force holding an electron to a proton in a hydrogen atom is about a trillion times stronger than the gravitational force between them. Measuring gravity's influence on quantum systems is like trying to hear a single pin drop in the middle of a hurricane. But it's not impossible. Physicists are designing experiments to look for tiny gravity-induced effects on quantum systems. Quantum levitated nanospheres, ultra-cold atomic clocks, and cold atom labs. Second, rethink foundational assumptions in theoretical models. For decades, quantum field theory has assumed a fixed, flat background spacetime. What if we build models where the geometry of space is dynamic and interactive, even at the quantum level? This is the domain of quantum gravity research, but let experiments guide the theory. We should ask, what kind of spacetime structure would produce the quantum effects we already see? Can we turn the problem around and use quantum mechanics as a clue to the microscopic structure of gravity? Third, look to the cosmos for answers. The early universe, in the moments after the Big Bang, had enormous energy density. Quantum mechanics and gravity were titans together on the same stage. Their echoes are imprinted on the cosmic microwave background. By studying subtle patterns in that light with ever greater precision, we might find signatures of quantum gravitational effects. The universe itself may have already run the experiment for us. We just need to learn how to read the results. Section 9. The shape of a unified truth. What would success on this path look like? It would not mean throwing away quantum mechanics. That theory is, and will remain, one of humanity's greatest intellectual achievements. Its mathematical machinery and predictive power are undeniable. Instead, success would mean finding a deeper foundation for it. We would finally understand why the world is quantum. The probabilistic rules, the uncertainty, and the superposition would no longer be brute facts about the universe that we must simply accept. They would be emergent phenomena, consequences of the underlying granular, dynamic geometry of space-time. Imagine finding that unified theory. It would be a single framework where general relativity emerges as the correct description of the large-scale average behavior of space-time, much like the laws of fluid dynamics describe the average behavior of water molecules. Quantum mechanics would emerge as the effective theory describing how matter behaves when it is buffeted by the microscopic fluctuations of space-time, much like the theory of Brownian motion describes a pollen grain being jostled by water molecules. There would be no conflict. The two theories would be revealed as two different approximations of a single, deeper reality. This new picture would likely resolve some of the most stubborn paradoxes in physics. The problem of black hole information loss might simply dissolve. The nature of dark energy might be related to the vacuum energy of space-time itself, a concept that currently yields nonsensical predictions precisely because of the clash between gravity and quantum theory. A unified view would provide a solid foundation from which to tackle these cosmic mysteries. Ultimately, a successful unification would change our very conception of reality. We would no longer see a world divided into particles in space. Instead, we might see a single, unified entity whose various excitations and configurations give rise to everything we see: matter, energy, and the geometry of the cosmos. The universe would be revealed not as particles moving through space, but as a dynamic tapestry of space-time itself, weaving and unweaving in a complex pattern that generates the illusion of both. This would be a profound shift in our cosmic perspective, a new level of understanding the world we inhabit. Section 10. A call to curiosity. Why gravity still beckons. The story of physics is a story of unification. It's a tale of realizing that seemingly separate phenomena, electricity, magnetism, space-time, are actually two sides of the same coin. The apparent conflict between general relativity and quantum mechanics is almost certainly the greatest challenge of unification we have ever faced. For a century, we have stared into this chasm, marveling at its depth. The path forward can feel daunting, lost in a fog of impenetrable mathematics and mind-bending concepts. But perhaps the first step is simpler than we think. Perhaps the first step is to return to the source of one of the theories and admit that our knowledge is incomplete. It is to look at gravity, that most familiar yet most enigmatic of forces, and recognize that we have not yet asked all the right questions. We have explored its majesty in the cosmos, but we have barely begun to probe its secrets in the quantum realm. The path forward is to be humble, to be curious, and to be guided by experiment. We must have the courage to build the machines that can listen for gravity's quantum whispers. This quest matters far beyond the esoteric world of theoretical physics. Every great unification in the past has transformed our world. Understanding electromagnetism gave us the electronic age. Understanding quantum mechanics gave us the digital age. Who knows what technologies and what new understanding of our place in the cosmos might spring from a true theory of quantum gravity. It could unlock new sources of energy, new ways to manipulate matter, or simply a more profound and beautiful picture of the universe and our place within it. So, the next time you look up at the moon, held in its orbit by the gentle curve of space-time, or ponder the miraculous technology inside your smartphone. Born from the strange rules of the quantum world, remember the gap that lies between them. Remember the grand puzzle, and remember that the key might not be in some exotic new dimension or undiscovered particle, but in a deeper appreciation for the force that started it all for Newton and Einstein. The path to a unified theory may be long and winding, but it may begin with a very simple, very powerful idea. We need to understand gravity better.